Hello everyone. Today we learn about the differential form of Maxwell equations, their derivations for the Gauss law of electrostatics, Gauss law of magnetostatics, modified Ampere circuital law, and what is displacement current. Now, differential form of Gauss law in electrostats. So in the earlier classes, we have seen how to derive the integral form of Gauss law. We'll be now deriving the differential form. So wherein we start with the integral form. So this is already we are aware of, and we will get to the differential form. So let us start with the differential form first. The flux of electric displacement vector D is given by surface integral D dot ds is equal to volume integral rho dv, where D is the electric displacement vector equal to epsilon E. Now where rho is volume charge density. Applying Gauss divergence theorem to equation 1, now see here left side is the surface integral, right side is the volume integral. So we have to use Gauss divergence theorems here to convert the surface integral to volume integral. So on the left hand side, if I use Gauss divergence theorem, I convert this to volume integral div d dv, which is equal to rho dv. That is the right hand side of this equation. So I take this to the left hand side, and as volume is arbitrary, I can say that div d is equal to rho, and this is the differential form of Gauss law. It is very easy to do. Now we next go to the Gauss law in magnetostatics. It states that isolated magnetic pole does not exist in nature, or magnetic flux lines form a closed path. If a bar magnet is cut into small pieces, each small piece will contain both north and south poles. Hence, flux of magnetic field across any surface is always equal to 0, which implies the integral form is surface integral b dot ds is equal to 0. We just use Gauss divergence theorem to convert this to volume integral, and we get div b dv is equal to 0, or div b is equal to 0. So this is your differential form of Gauss law in magnetostats. Third Maxwell equation is the Faraday's law of electromagnetic induction. So we'll find its differential form now. According to Faraday's law of electromagnetic induction, an induced EMF is produced in a closed loop, which is defined as negative rate of change of magnetic flux. So as I mentioned earlier, phi is the symbol for magnetic flux or electric flux. So here we are talking about magnetic flux. So E is equal to minus d phi by dt. And we also know that magnetic flux is surface integral b dot ds, where S is any surface having loop as boundary. So the induced EMF is equal to, by substituting the value of phi, we get minus d by dt integral v dot ds. We take d by dt inside, that becomes induced EMF is equal to minus integral dou v by dou t ds. That is equation number 1. Now we also know that E can also be computed by calculating the work done in carrying a unit charge round the closed loop. So induced EMF can also be written as the line integral E dot dl, that is equation number 2. Now equating the equation number 2 and 1, we get integral E dot dl is equal to minus integral dou v by dou t ds. Now we see here we have line integral, and here we have the surface integral. So we will convert this line integral to surface integral using Stokes theorem. So we get integral curl E ds is equal to minus integral dou v by dou t ds. This is as it is, right hand side. So we get surface integral curl of E plus dou v by dou t ds is equal to 0, or curl E is equal to minus dou v by dou t, which is the differential form of Faraday's law of electromagnetic induction. So you can get back to the integral form using the same derivation in the opposite fashion, starting from curl E. Now we'll study the last and very important Maxwell equation, the fourth equation, which is called the modified Ampere circuital law. We know that Ampere circuital law states that curl H is equal to J, where B is equal to mu naught H. You can look here in this equation. So this is equation number 1. We take the divergence from the left hand side and right hand side both. We operate divergence on both the sides, we get divergence of curl H is equal to div J. Okay. Now using the vector identity that divergence of curl of a vector is equal to 0, we get left hand side to be 0 and right hand side can also be written as minus dou rho by dou t. How? That is from the equation of continuity where we got divergence J is equal to minus dou rho by dou t. Therefore, we get dou rho by dou t equal to 0, or rho implies the constant of static field. So that means the old Ampere circuital law was valid only for a constant field or static field. Now, Maxwell found out that it does not include the time varying electric fields, as time varying electric fields may also produce magnetic field. Hence, in order to make Ampere's law consistent for the time varying fields also, Maxwell suggested to add a new term called JD. It is dimensionally similar to the J. So he called curl H to be equal to J plus JD. Now, by doing simple mathematics, we'll find out what is the value of JD. We again take the divergence on both the sides. Now, on the left hand side, we again use the vector identity divergence of curl H is equal to 0. And right hand side becomes divergence of J plus divergence of JD. Therefore, divergence of JD equal to minus divergence of J, which is also from the equation of continuity equal to dou rho by dou t. But from the Maxwell equations, rho is equal to divergence D. That is the first Maxwell equation we learned. So we substitute back here and we get divergence of JD is equal to dou by dou t of divergence D, which is divergence of dou D by dou t. Therefore, if we equate these two, we get JD is equal to dou D by dou t. Substituting JD in equation 2, we get curl H to be equal to J plus dou D by dou t. Now, this equation is called modified Ampere circuital law. Curl H is equal to J plus dou D by dou t. Now, we have come across the new term which is called displacement current. Now, the new term JD, which is equal to dou D by dou t, is called displacement current since it is time rate of change of electric displacement vector D. From the above equation, it is clear that it is equally capable of producing magnetic fields as the conduction current density. You see here, dou D by dou t also contributes in curl H. The displacement vector D is linked with the electric field E. Therefore, it becomes indirectly time varying electric field. This displacement current is responsible for the production of magnetic field in empty space where conduction current is 0. Few characteristics of displacement currents are as follows. It's the current only in the sense as it can produce magnetic field. It has no other properties of current. Its value is finite in perfect vacuum where there are no charges. Its value in good conductor is negligible in comparison to conduction current at any frequency lower than the optical frequencies. It helps to make the net current continuous across discontinuities in conduction current. Displacement current arises only due to variation in displacement vector D. When the variation in D vanishes, the displacement current also vanishes. So this was all about today's lecture. Thank you.